Hi everybody, I'm Giuseppe Di Giulio. Today I'm going to talk about complexity of mixed Gaussian states from Fisher information geometry. This talk is based on these two works made in collaboration with my supervisor Eric Tonni. Let's start by defining the circuit complexity. We consider a reference state psi r and a target state psi t, both pure quantum states, then a quantum circuit which allows us to construct psi t starting from psi r. This quantum circuit is made by a set of unitary gates that are drawn by a given set of elementary gates. So the complexity is defined as the minimum number of allowed gates that is needed to construct the target state starting from the reference state. And recently, the high energy physics community has been interested in this complexity because the following reason. It's known that the holographic entanglement entropy is not enough to capture the late time dynamics behind the horizon of a black hole. For this reason, Susskind and collaborators started to look for quantities with this property. And there have been some proposals, like for instance, the one we call CV, which is proportional to the extremal volume contained in the codimensional 1 hypersurfaces contained in the bulk, which is denoted here in blue, or the other one, which is proportional to the gravitational action evaluated on the Wheeler-DeWitt patch, that is these blue shaded regions. Then it's been conjectured that both these gravitational quantities are dual to the complexity of the CFT states at the boundary of ADS. For this reason, understanding complexity in conformal field theory and more generally in quantum field theory, it's become an interesting problem and still to be understood completely. So the way we are going to approach this task is to compute the complexity for a lattice model with a known and understood continuum limit. For this reason, we consider the harmonic lattice characterized by this Hamiltonian on a d-dimensional lattice. And we chose this model because the continuum limit of it is a Klein-Gordon field theory that in the continuum, when omega goes to 0, is a conformal field theory. And in particular, on +1 dimension, we have that this conformal field theory has central charge C equal 1. Moreover, we restrict our attention to the Gaussian states, which are the states of systems described by this Hamiltonian, which are uniquely determined by the covariance matrix, which is a 2n times 2n symmetric matrix, whose entries are given by the 2-point functions of the operator qi and pi determining the Hamiltonian of the model. Moreover, this matrix gamma is to satisfy the uncertainty principle, which is implemented through this constraint on its eigenvalues. We are going to follow the approach by Nielsen, goes back to 2006, for computing the complexity, which is a geometric approach that basically corresponds to considering a quantum circuit connecting two generic mixed states and see this circuit as a curve on a manifold in which each point corresponds to a quantum mixed state. So in this geometric picture, the optimal circuit can be seen as the geodesics, and therefore the complexity is the length of the geodesics. So we have a nice and powerful geometrical method for computing the complexity, but it has some ambiguities, and it is related to the choice of the cost function, namely to the choice of how we weight the different gates in the different directions of this manifold. The analysis has been performed first for pure states by Myers and collaborators in this series of papers. So we are going to develop an approach for mixed state based on this geometrical picture. And in particular, for the states we are going to focus on, which are the bosonic Gaussian mixed states, we consider a reference and a target state described by two covariance matrices gamma r and gamma t, and then the optimal circuit is given by this expression. And then for every value of S along this curve, we have a point that corresponds to a bosonic Gaussian mixed state with covariance matrix given by GS. And once the optimal circuit is known, we can compute the complexity as the length of this path and proportional to the so-called Fisher-Rao distance. So in our work last year, we have, through this approach, we have proposed some expressions for the spectrum and the basis complexity. Once we deal with the mixed state, a possible application is the computation of subsystem complexity, which is defined as follows. Consider a pure quantum states defined of a bipartite Hilbert space where HA contains the grid of freedom of a spatial region A. Then the reduced density matrix ρA can be computed, and if the state ρ is Gaussian, then also ρA is Gaussian, and then it is uniquely determined by a covariance matrix, which is called reduced covariance matrix. So the subsystem complexity is simply the Fisher-Rao complexity between two reduced covariance matrices. And as an application in the paper of the last year, we consider A the bipartition given by A is an interval in the infinite line, and we compute numerically the complexity, finding that for L large enough, this quantity grows proportional to the square root of L, meaning that it fills the volume of the subsystem and not the boundary. This is a typical feature of the complexity. Another application is the temporal evolution of the subsystem complexity after a global quantum quench, which is one of the most known protocol for driving a quantum system out of equilibrium. And it goes as follows. So at time t equals 0, we are in a ground state of an Hamiltonian with a frequency omega naught. And then when t is greater than 0, we let the system evolve through an Hamiltonian with a different frequency. And so this leads to a non-trivial time evolution that preserve moreover the Gaussianity. And so we can apply our machinery for computing the complexity of Gaussian states for detecting its temporal evolution. Moreover, we focus on the massless case, so when omega is equal to 0, which has an underlying conformal field theory description in the continuum limit. And also holographically, there are some results in the Baedia spacetimes that are backgrounds employed as a gravitational dual of the global quench of the CFT at the boundary of ADS. Here we report some numerical results for the temporal evolution of the subsystem complexity after the quench. The reference state is chosen to be the initial state, while the target state is a state at generic time t after the quench. And we consider two bipartitions, namely the interval in the infinite line and the interval in the semi-infinite line with the Dirichlet boundary condition at its origin, where the interval is separated by a distance d from the boundary. And here we compare the complexity with the increment of the entanglement entropy. And we report the numerical data for various values of L, and we see that for L large enough, these data collapse, meaning that the curves we are looking at there are some results in the continuum limit. Here we observe, for example, that initially these two quantities have a different behavior. In particular, the complexity does not discriminate if d is equal to 0 or different from 0, while the entropy does. And the reason is that d equals 0 corresponds to a bipartition with just one endpoint, while d different from 0 has two endpoints. And as we know, the entanglement entropy fills the number of endpoints, while the complexity that fills the volume of the subsystem does not fill the number of endpoints, but only the volume. Moreover, while the initial growth of the entanglement entropy is linear, and the one of the complexity is linear only at the very beginning, and then it deviates from linearity, exhibiting this local maximum. Then after this, there is a mild logarithmic growth in the intermediate regime. And then for t greater than L plus d, we observe the saturation of both these quantities. That is due to the following physical fact, that for time large enough, the reduced density matrix of the system relaxes to the generalized Gibson submod for the particular harmonic chain that we have considered. These results can be compared with some holographic results, and this comparison can be only qualitative, and the reason is that our underlying conformal field theory has central charge C equal 1, while the holographic results are obtained for CFT with C much greater than 1. So here we compare our result in the continuum limit with some result for the holographic subsystem complexity in the CV proposal obtained by Auzian collaborators and Chen and collaborators. So here we see that for early times you have some common features, like for instance that after the initial growth, both the results exhibit a local maximum and then a decreasing. And then there is this point in which the regime changes, that is approximately 3 over L equal 1/2. And this value of time is exactly the same, both on the lattice and holographically. Then we have also another common feature that occurs in the initial time regime, and it is the following. The local maximum that we see is an 8 that is proportional, let's say, increases with omega 0 when for the lattice results, and with m in the holographic results, where m is the mass of the collapsing black hole. And the important point is that both m and omega 0 correspond to the same physical interpretation, which is the quantity of energy injected in the system by the global quench. Then, while for initial time we have qualitative agreement and similarities, for t greater than L half, we have a different qualitative behavior, because in our lattice result we see a mild logarithmic growth. And here we see for these black points that are the one obtained for the interval in the infinite line, which corresponds to this holographic, to the setup of these holographic results, while the holographic results for large time really saturates, goes to a constant. So to To conclude, we have evaluated the complexity for circuits made by mixed states, exploiting the Fisher-Rao distance. And as an application, I showed you some results for the temporal evolution of the subsystem complexity in comparison with the one of the entanglement entropy after a global quench. Remarkably, we have observed a qualitative agreement with holographic results for the subsystem volume complexity. This agreement occurs at early times, while at late times we see two different qualitative behaviors. As a future perspectives, we can surely investigate other quench protocols, like for instance the local quench, or exploring other geometry of set of mixed states, like for instance, consider non-Gaussian states, or more interestingly, also the complexity of fermionic mixed states. Thank you.